And guys, these models that we're doing in Python and the code that we're writing and these functions, these are things you guys could do by hand. So that's what I meant by automating it. You could calculate them and write them out and, try to predict the probability, by hand, step by step by step. But programming is just a way that you can keep on doing it repeatedly, but changing the outcomes, trying out different, features for people, like different cholesterol levels, different ages, genders, body mass index, you name it, like any different features. And this is just an example from one model, but you can apply this to other predictive models that you come up with. I generated those models using R, which is statistical software, and sometimes you can just directly call the prediction, you can call the model and just directly make predictions. But this is just in general an example of how you can write functions in Python, how you can make predictions, and how these models can give you predictive abilities. So just bringing some more life to these predictive models that we're talking about, and how behind them there's clinical meaning. And we often take existing patient outcomes and mean data, and then we try to predict the probability of them having certain outcomes using that. Like we are predicting the probability using the simple logistic regression model that a patient will have coronary heart disease, given the serum cholesterol level. So just one part of it. But then for the complex one, we not just take the SCL, but we're taking like many other features as well, like the blood pressure, age, gender, body mass index is as well. So it's all about like what you want to focus on, but that is a little bit slow because we do need to collect additional information on the patient as well. So there are pros and cons to each approach, and we want to find the one that will be the most effective. And we have to figure out how to train our models effectively. So what I was just showing you is a way that you guys can also experiment without having to repeatedly do all the calculations out. This is how you can use programming and Python as a calculator and then see how things change based on different parameters, different inputs, different ages, numbers that you put in as well. So that's what I meant. But this, of course, you can definitely do this by hand. There's no reason why you can't do this by hand. And I've shown some examples doing this by hand as well. But this is just a faster way, and it also shows you programming and allows you to kind of connect everything together and try out different iterations much faster. And I also kind of want to show you how we can take this simple logistic regression model for predicting coronary heart disease that I mentioned. This is the predicted probability that a patient or individual has coronary heart disease based on serum cholesterol levels. So this is a little robot bug that's trying to learn, e to this negative 2.74 plus this. And, you can try to figure out what is the probability that this patient has coronary heart disease given some serum cholesterol level. And pretty much what you can see is that this is E is Euler's number. So you need to get this number from the importing the math package in Python. And then if you call the math exp1, this is just E to the 1 power. That's what this is. This is just E. Oh, let me just write this in bed. It's just E to the 1, which is just equal to E. That's what this is. So then what you can do is you can just see that this is the same equation here, e to the some power. And like, for instance, if we do 4 times, this is exponent. So 16, this is equal to 4 squared, that this is equal to, 4, and then with the exponent 2, that's what it's equal to 4. This is the first argument is over here is 4, which is, the base, and then this is the exponent that you want to raise it to. So what we can do is we can just write this as a formula. We can just write the simple logistic regression model as a formula here. We can add a new cell, and we can just see that, the numerator. So we have some serum cholesterol level, total cholesterol, let's, like this, be consistent. So let's just say this is like 200 here, 200. And what we can do is we can just say that the numerator is equal to negative So this part is being raised to this value here. We can just say that we can just call this term here a constant here. We can just call this, like, let's just call this some variable, like we can just call it exponent val. So let's call this exponent val. The exponent val is this part here that I've highlighted here. Its exponent val is this right here. Ah, Christmas colors, yay. So we can just call it exponent val is equal to, and we can just take this number. This is right from above. I just noted it down. This part here plus, and whatever this is all multiplied plus this. And you can't do parentheses multiplication in Python. You just have to just do it like this. You have to just do the asterisk multiplication. So exponent val would be something like, oh, this is just a negative. Okay. You have to be careful sometimes. Okay, no wonder it's looking kind of weird. So this is the exponent value here that we get. So this is the numerator, like not the numerator, but this is the exponent part that's being used in both locations, like right here, and also like right here too. That's exponent val right there. So then what you want to do is you want to see, okay, well, we just need to raise e to this power. So we have this e that we've defined. We just need to raise e to this power here of exponent val. So, and that's the numerator. So the numerator is just e. And remember how we can do 4 squared, right? This is 4 squared. So we can just do numerator is e to the exponent value. That's a numerator. So that's literally giving this part here. So this part here is just given by this here being raised e to that numerator value. So that's what the numerator is. And so we have to define e again, and this here, and we can have the numerator here. And then similarly, the denominator is just the same thing as the numerator, but just have to add 1. Whatever you have in the numerator, you just have to add 1 to that, and you'll get the denominator. So this is just 1 plus numerator. So we have a denominator. So I'd like to also add print statements. Print, please note, numerator is and the fraction. This is the predicted probability CHD is equal to just numerator divided by denominator. And you can just call it here. And because it's a probability, it should be between 0 and 1. We can just, kind of multiply this by 100, and then we'll have a percentage. So we can do print. Please note that the risk of CHD for a serum. This is another way you can also have, these print format. So see, like for instance, and you can also add Oh yeah, yeah, my bad. If serum cholesterol level of see with the printf format, you can put the variable also inside the inside these curly brackets. That's another way you can write it. If 200 is, and then you can just kind of put in the variables because you have an F in front. It's called a format. You can put this here, and then you can just also add your percent sign. And then you can also have the variable my name. So this is how you can print out the predicted probability, of given like a serum cholesterol level of 200. So how does that realistically work out? So let's say that we have this at 200 here. Then let's kind of map this across here, and we can kind of see that, okay, well, it does seem like it's about halfway between, so this is 30, it seems like it's kind of halfway there. So it does seem like 26%. So for a serum cholesterol level of 200, 26% does seem, pretty reasonable. So again, that's how you can represent this, and you can kind of come up with like a little function that's called, so this is a function. So anytime you want to keep running this, you can call it simple logistic regression, CHD probability. And then what you will need is my name, because I'm calling my name here. We also need the SCL level. So it just needs very little information. So we can just call this input inside here as well. This is what E is. We had this exponent value here. We can just migrate all the code in here. This part is given from the logistic regression. This is from specific to our logistic regression model. And then we just have this here, a numerator and then denominator here. And what we can do is we can just return. We don't have to have this here. We can also have, we don't need to print these out, but we can just do return predicted probability. So that's what it will ultimately return to us. And what we can do is we can just run this here. If we want, we can have something like we can have a default. Oh, actually, we need to then move this behind. We can have it like, maybe we can have a default SCL of like 200. That's how you can set a default so that, even if it just has, it doesn't necessarily need an SCL, but you can also put like 203. And this is it returning something. So we can do CHD risk, and we can assign it here, and it's going to print out the statement. But if we call CHD risk again, it got assigned this value, which is the same thing as this predicted probability of CHD. So, oh yeah, see, please note that using the simple logistic regression model, and now we can just run it again and see that, is this. If we change this up to being like 400, which some individuals had, it's 65%. So for 400, we can also map up and see if it's that high, like 400, like where does it typically fall? Let me try to be more precise. This is on 400, and let's see where it falls. Yeah, it's 65%. Yeah, this value right here is it seems feasible. 65% is right there with that serum cholesterol level of 400. So again, these are all like patient values that we got from the Framingham-Hoyt study. And this is red is the model that we learned that we can visualize here in multiple dimensions. It's much harder to understand or even visualize it because there's so much going on. So at 2 dimensions here, this is just one variable, so we can visualize it. And this is another example of how you can, quickly, see if you have a bunch of patients and their, information on them. Like let's say that you have a set of information on patients list, and let's say that you have a list of the names, and you can have no, I don't want to be that pessimistic. 300. I'm on. Hypothetically, let's just say bug and okay, so we have all these people here, and we have Santa who might have a higher cholesterol. He loves cookies. Okay, and then we want to go through. So this is patients list. So for I'm on DD okay, and then we can print patient. So patient name equals patient at 0. So it's the 0th element in the list, which is going to be this for each patient, it's going to be this first set of values. Patient name here. Print patient name. Oh, no, so it's getting the first element, a list of lists. So the length of this is going to be 6. And then you can print this out here. You can print the patient name. And then you can also print, like SCL patient is equal to patient and then 1. And we can also print this out here. And then we can just run this here. So CHD risk is patient name. We don't need the name, but it's just something cute to have. So we can have patient name here, and then we can also just have outcomes list. And then what we can do is we can just do outcomes list. This has patient name, SCL, predicted probability of CHD. And what we can just do is we can just append. So outcomes list dot append. We have patient name, SCL for patient, and then CHD risk. And then when we finish the loop, we can just see what this looks like. So because the code naturally prints out, a print statement, which you don't need to include it, you will see this here. And you can just see that it's a list of lists. If you want to make it nice and cute, what you can do is you can also use something that's known as pandas, import pandas as PD. And then you can make it into a nice data frame. So simple logistic model CHD predictions DF, it's a data frame, is equal to pd.data frame. And then we can put this in here and have call the columns, which we have as patient name, SCL. So this is patient name, this is name, SCL level. And this is probability, CHD probability. And we can have, and we can also just add in a quick variable that's just called model used, and then we can just set this equal to simple logistic regression model, which will just make sure that every row has this variable that's known as simple logistic regression. So basically this takes a list of lists, and each of these lists is one row. Sanya, I'm on DD, Pug, Dad, Santa, and you have name, SCL level, CHD probability here. These make if you did not have this here, then you would not have any column names. So having this allows you to have names for the columns. And then adding this in here allows you to just have, see a simple logistic regression model. So CHD probability, let's also add, percent. So that we remember that it's all a percent. And we can see if your CHD level is 300, what is your percent of, CHD based on the logistic regression model, the simple one, for all this information here. 250 is like 35%, which, if you look up here, 250, 35%, seems pretty reasonable here. So you can see it all maps to these values here. So you can see how as this changes, we can also predict CHD probability, all by using this function that we have defined called simple logistic regression. And we can very similarly also just do this with a complex model below. So it's more of a monster. You can see that it has gender, BMI, age, SCL, diastolic blood pressure, SBP. So it has like a lot of variables here, but it's the same idea. So we have SCL here. We also have gender. We can get rid of this here. And I can just use it simple. This is complex. And using the complex. Okay, so we have gender. So let's start with everything here. So we have gender. We have BMI, body mass index, age, SCL, DBP, SBP. So this just shows how different predictive models come up with different predictions for your risk and which one is better. That's what we have to also figure out, which one is better. And I have written down what this numerator is, this exponent val. Again, so that's what we want to set exponent val to be. You just want this exponent up here. This exponent val will be what this needs to be. So we just need to update this. But specific to our logistic regression. So that's what usually changes time and time again. So I'm just going to take this part here. I've written it down again, and I'm just going to take this. And I'm going to just, let's see, I'm going to just go here. And I'm just going to make this negative minus. I had just copied it from the web. So that's fairly long, but you have to remember that this has to be times gender. And you can also have like different variables too for this. And plus BMI. You can also have like a BMI variable part times this times BMI. Plus this part times age. I just copied it from Word, which gave me the original equation, just so that I don't have to remember all these decimal points. So that's why the formatting looks a little bit odd. Times DBP. That's what this asterisk means, multiplication, plus this times SBP. And this is all we've got everything. So again, this 0.00794 comes from up here. And I think that should be it. Those are the main differences here, but we now need a lot more information. So now I also need to provide information here. My name, gender, BMI, I'm not too sure. Let's just say 20, for instance, I'm not sure. Age, just say 28, SCL. Diastolic, well, what did I go with here? 300. Okay, let's just go with 300. So now we also see that I have my same name and SCL, but let's say I'm providing more information. Diastolic blood pressure is 130, for instance. Systolic is like 80. Okay. Oh, sorry, gender has to be 1 or 2 based on the model. So gender is one, or actually we can also have an if statement. So let's say female is what we put in here. And then what we can have is if gender equals female, gender val equals 1, else maybe gender val equals 2. This is for male. So people forget what the coding is. Then you can just say, okay, this is the how we use it. So you see, that's what it was saying, that, you know, gender is female, but how can you multiply female times a number? So that one was what it was complaining about. So now we can see that I have a 33% chance of coronary heart disease instead of 45%, which by the simple logistic regression model. But yes, I do need to provide all this information on BMI, age, SCL, diastolic, systolic blood pressure. So we can also have like Santa here. We can have male, BMI maybe, you know, 40, age is 101. Not sure about the blood pressure levels. So maybe if giving this like 400, for instance. And you can see that this risk for Santa really goes up. So what did I say for Santa before? I said 415. Okay, let's make the serum cholesterol level 415. And then you can see how it changes. So this is what, you know, the instead of the risk, this should be called predicted risk. That's a predicted probability that you have CHD. So again, this should also be predicted. So that's what you can do. You can run it for, you just need like a lot of information, and then you can, you know, you would need the BMI, age, SCL, diastolic and systolic blood pressures, and then you could make predictions here. You know, so instead of predicting Santa has a 68% simple logistic, you instead predict 82%, which is so much higher using the complex model. But for me, instead of predicting using the simple that I have a 45% risk of CHD, you instead are predicting much lower, like 33.9% using the complex model. So this is just examples of how you can come up with functions. So this is a function. To predict HD risk. So you can also add these method headers as well. So this will also be very helpful, you know. So please note that helps calculate the predicted probability that a patient has coronary it uses logistic regression. My name, the name of the patient, to be friendly. Gender, male or female. BMI, body mass index. It's a numeric variable, so it can be float. And then age in years. SCL, serum cholesterol level. BDP, which is the diastolic blood pressure. SPP, which is systolic blood pressure. And then it returns a predicted probability of CHD, which is predicted probability that this individual has CHD based on these 6 different features. And yeah, you can definitely make these predictions for a bunch of individuals. You know, you can just call this, you know, if you have any individuals, you can write a loop and you can just figure out what are the chances, you know. So let's just come up with some random person. Squidward, tentacles, and SpongeBob. We slightly on the thinner side. I guess 20. And let's say maybe his age is this, his blood pressure is probably pretty high thanks to SpongeBob. And his systolic is also maybe 101. So it's kind of high squared, but please note that using, not just serum cholesterol level for is this, and then you can just run this here. And then you can just also have a predicted risk is this. And if you want to, you can also just have what these variables are that you input it. But, this is a predicted risk. You can also see the predicted risk of CHD is 33, 82, 78%, BMI. So you can also add in more statements and if statements here too. And you can also like print out given this cholesterol level and so on. But I just sort of wanted to show that these are how you can play around and use predictive models and change all sorts of inputs to see what are my risks of, what is the risk of having, advanced, stage of coronary heart disease. You can use a bunch of predictive models. So we talked about decision tree classifiers and how you can have functions here. The same function is essentially returning CHD risk here, which in each step, you're sort of going through this tree and identifying different variables and trying to predict your risk of coronary heart disease using a decision tree. You can represent this tree in code as if-else statements. And oftentimes when you're learning programming, you probably see that this is how you write if, else, if statements. So if this branch is true, you go along it. Otherwise, you go along the other branch. So you can make predictions with Santa and certain, different attributes. Like this is a total cholesterol or systolic blood pressure. You can make all sorts of predictions of coronary heart disease, like high. You can just have a high versus low. You can even have numbers. You can have buckets of bins, like 20 to 50% is one range, and 50 to 70%, for instance. You can have multiple bins. You can also have a simple logistic regression, which just takes one variable, so we can visualize it here, unlike the complex one that is too complicated that we can't really visualize it well. It has 6 variables, so 6 different dimensions. So it's like 1D, but we have the predicted probability. So, and these are the actual outcomes in black. These are the patients. And you can see that they have 2 outcomes. Either they have a CHD after 10 years or they don't in reality. And that's why we have to use a logistic regression model to try to approximate this as a probability based on the SCL level. So we can try to write this using E. This E is the natural number. E is 2.7. And we can write a simple logistic regression model that just has, this predicted, and you don't even need name. It's optional. It just makes it nice and friendly. And again, this input is a great way to take user input from the user directly. That's what input does. So again, input provides it there so that you can just say, and then you can just run it again and see like it's just gonna say, hi, buddy. And then we also saw how you can kind of construct, a data frame of the predicted outcomes here. For the simple one, it's just SCL. For the more complex one, you would definitely need more information on that. You would need, gender, BMI, age, serum cholesterol level, diastolic blood pressure, and systolic blood pressure to come up with these predicted probabilities. So you need quite a bit more information. And hopefully this can show you guys how you can construct, functions using code. And this can even help you guys with your math homework. I hope you guys will actually consider that, because you can automate your math homework. I mean, while you're getting better at computer science, hopefully your math won't go down because you're not automating all your homework away. So it's like computer science skills up and, math skills, those were the good days of math where you could automate stuff, or you could, do a lot of sums, and then math kind of, it's a great subject in the end, but you need a lot of tenacity to go through it, I feel. But I just wanted to show you that these are predictive models. So it's like a fortune teller trying to predict what are your risks. Which model is ultimately good in the end? Well, we have to let time and fate kind of check, on unseen data. And that's why it's good to have models that generalize well and that can try to figure out and pick up the patterns in the data. So we can hopefully predict the risk of CHD accurately for people and they can act on it. Otherwise, we'll be having a lot of errors like false positive, falsely saying somebody has a coronary heart disease when they don't, or a lot of false negatives, predicting somebody doesn't have CHD when they actually do. So talking and choosing of these predictive models is going to be the focus of many of my videos. And I'll be talking about different methods like decision curve analysis, where we can try to select among these different predictive models. So please let me know if you have any questions at all. And thank you guys so much for listening. And I really hope that this helped you guys out.